Thank you very much. Welcome, everybody. This is project number, I don't know, but the first lecture of it, it's a project together with Athreya, who sits there in the third row in the middle. And we are having a project on local limits of uniform spanning trees. And for today, I would like to just give you an introduction into the topic and also the set of problems which we have assigned for the group. The uniform spanning tree is a model from statistical mechanics. It's quite interesting. You do it usually on a graph which is finite and connected, and it tells you a lot about geometry in the graph. A spanning tree itself is just a connected subgraph of this graph, which uses the same set of vertices, but not all of the edges. In fact, it's defined in such a way that it's spanning the graph if it uses all the vertices, and the edges is such that the graph is still connected, but does not have any loops. And that means in particular that if the graph has initially n vertices, that the uniform spanning tree has n-1 edges. So if you have not seen this, this is very easy to see. Just think of any arbitrary point as the root, and then every vertex has an edge pointing towards the root except the root itself, and this way you have this one-to-one mapping which counts in the end n-1 edges. A uniform spanning tree, as the name is suggesting, is just the uniform distribution on the finite space of all of the trees spanning this graph. And one of the examples which we will encounter in the problem, which is the most simple example, is the complete graph, because it doesn't carry any geometry here. All the edges are present. And if you look at the uniform spanning tree of this one, then you clearly get the uniform tree, because any edge has the same probability to belong to that uniform spanning tree. And it's a uniform tree with precisely n vertices. And it's known, and this is something I'm going to tell you more about tomorrow, that this has the same distribution as a branching tree when the offspring distribution is whatever, lambda positive, but conditioned on total progeny n. What we are going to use in the whole project is studying random walks under certain questions. And the reason is that random walks are very nicely linked to the uniform spanning tree in different ways. And one of the most important ways, of course, is that you can use them to generate your uniform spanning trees. So when I say a random walk, then I always mean a Markov chain with values in the vertex set, which jumps to every neighboring point with the same probability, 1 over the degree. And there are many algorithms known. It started not just with David Aldous and Broda, but also people from computer science who evaluated the matrix, I forgot the name, matrix tree theorem or something, to read off this algorithm. And David Aldous just turned around the time and brought more nice algorithm. But in the end, it's Wilson who come up with an algorithm which will be very important as a tool for studying what we want to study. And Wilson algorithm is based on loop-erased random walk, which is also a very nice model in statistical mechanics. It was studied by Greg Lawler in his PhD thesis. It was the main topic of his thesis, and he is also leading expert in this model. And the motivation for him to study this, or for his advisor to give him to study this, is that people were interested in another model, which was self-avoiding random walk, which is a quite interesting model. Both models have in common that they create paths which do not have loops. And self-avoiding random walks very difficult to study, so they thought maybe they do a bit of a lighter version, namely the loop-erased version, in order to approach the self-avoiding random walk. This motivation failed because the models are quite different. But anyway, this is still a very interesting model with yield a lot of results. It's defined as follows. If I have given a path segment with values in the vertex set, let's say of length m, on a locally finite connected graph, then I can define the loop erasure by literally just erasing the loops chronologically in the order that they appear. And I have here small picture. Now, if the path goes like this, you see it's the yellow one which creates the loop, which we erase. And then when the blue path crosses this yellow one, it doesn't see it because it is erased already. So what you see in blue would be the loop erased version of it. Usually you take for this path gamma a random walk as a driving process, and then you call the whole model the loop erased random walk. And it is not hard to see that if the walk is transient, then no, you don't have to do this only for a finite path segment. You can actually extend it easily for an infinite one, because the point of transient graphs or transient walks is that you see each point only a finite number of times. You do not keep erasing the same loop over and over again. So for transient, everything is fine. Here's Wilson algorithm. Wilson algorithm does the follows. It works for finite graphs to begin with. And what you do is you pick two vertices, V0, V1, in a very arbitrary way. Now, there's nothing given. You might think about V0 as the root, even though the graph doesn't need a root, but let's think about it for a second. And then what you do, you start a random walk in V1, and you let it run until it hits V0. Now, you get a path segment of a random walk, and you do the loop erasure. You take away all the loops in chronological order, and this gives you a branch, which is loop 3, which you take as the first branch of your tree. And then again, in a very arbitrary way, you pick a vertex V2, which might be even on the tree. Never mind. No, just take another one, and then run a random walk until it hits the branch, which you have already created. This goes usually much faster, no? Hitting a point is harder than hitting a branch. But once you have done this, you again loop erase, and you do this recursively. That means conditioned that you have already created k branches. You pick a vertex vk plus 1 and run the random walk, starting in that vertex independently of everything which happened before until it hits the tree which you have created so far. And you can do this. It's a finite graph. If you choose your vertices clever, then at some point you have chosen all of the vertices. You stop if all of the vertices are included in the tree. And this kind of algorithm, as you can see, can be extended to locally finite, infinite graphs, if the graph is recurrent. Here you need the recurrence because here you want to make sure that you're actually hitting the points you want to hit. Okay, so here's a very small example, which you saw already in January's talk. It's a graph which 6 vertices, and assume that your first walk goes from F to C to B, and then it has a loop via E, and then it goes to A. So what you would do, you would first of all take away this loop and keep just this loop erased path. And then this is how your first branch looks like. And then let's say you start from D until it hits, in this case in B. So you would add this branch. And in the next step, you would take the vertex E, let the walk go until it hits here in C, and you would find finally the uniform. You would finally find the spanning tree. It's obviously a spanning tree, which Wilson algorithm gives us, and it's the theorem of Wilson who proved that the law of the random walk, the output this algorithm gives, is always the uniform spanning tree, which is quite nice, and it also shows that it does not depend on the order or the way that you have picked your vertices. You are very free in doing this. And as a corollary, but nevertheless important, is that if I have a finite connected graph, I have 2 different vertices, then the law of the unique path connecting these in the uniform spanning tree equals, of course, the law of a loop erased version connecting these 2 vertices. It's a loop erased path which are connecting them. Okay, so Wilson algorithm has a couple of nice consequences, which reprove existing results, but in a very short and efficient way to understand. And the first of this is if we have a finite, simply connected graph and an edge from X to Y, then the probability that this edge, which is an edge in the original graph, also belongs to the uniform spanning tree. This is 1 over the degree of X times the probability that you see the other end of the edge. If you start your random walk on X, you see the other end before you actually return to X. And that's something you can see very easily from Wilson algorithm, because you just wait until, I think, what might happen is that you go from X to Y, but then you close a loop and you take the edge away. But the last time that you have done this, you have the possibility that you either go from X to Y directly, which happens in probability 1 over degree of X, or in order to have this edge from X to Y, you can also go somewhere else, but then you have to return to X before you actually go to Y. And then you start the problem again. It's a recursive equation, and if you rearrange, then you find this formula. It's very nice. It's one of this original paper of Kirchhoff I'm going to talk about tomorrow, which is almost 200 years old. We had this result already, maybe in a different language in terms of resistances, but the nice thing about the algorithm, you see it very straightforwardly. There's another thing which you can see from Wilson algorithm, and that's the spatial Markov property. And the spatial Markov property says something about the law of the uniform spanning tree, given that you know that certain edges belong and certain edges do not belong. And this you can also understand when looking at the Wilson algorithm, because assuming that you know the edge x, y does belong, then if you run your algorithm at some point x and y are in one of these branches and you want to hit them, then it doesn't matter whether you hit x or y. And therefore, you can as well identify them. And the other thing is, if you know that a certain edge does not belong to the uniform spanning tree, then the random walk should not pass it. So that's the same as actually taking it away from the original graph, so the random walk has no chance to try to use it. And therefore, the result reads as follows. If I've given two subsets of edges, A is such that this is the set of edges which is supposed to be there, then it should clearly have no cycle. So you take an edge set without cycles, and you take a subset of edges B, which is the one on which we want to condition that they are not there. So if we want that certain edges are not there, we have to make sure that we don't disconnect our graph. So we will assume that B is such that the graph G minus B is still connected. And if we do it this way, then Wilson algorithm tells us that the uniform spanning tree G conditioned on the event that all the edges in A are there and all the edges in B are not present equals the law of another uniform spanning tree, but of a slightly modified graph G. And in that modification, you kind of contract all the edges in A. Each edge in A has two endpoints, you just identify them. And it also, after doing this, takes away all the edges from B from which you want that they are not there. Usually, if you start with a very symmetric graph, or graph with lots of symmetries, such a conditioning kind of breaks all the symmetries, so it doesn't seem to be very useful, but latest, if it comes to comparison arguments, it's quite helpful result, which you can read off from Wilson algorithm. Okay, so that's what we want to do is we want to study local limits of uniform spanning trees. Yes, sure.
So when we say that we contract the edges in A, so basically every connected component in A becomes one point.
Can you say again? I'm just.
When we say we contract the edges in A, does that mean that every connected component in A becomes 1 point, like something like that, basically?
Yes. Yeah. You just identify the endpoints, but if they are connected, then it's basically 1 point.
Cycle that will become.
You're right. By the way, please ask questions. It's more about that everybody, I do it slowly today, everybody understands a bit the questions and the main tool in the project, rather than understanding the whole literature about it, what is known and what is not known. Okay, so we are studying local limits of graphs, and local limits is something which in the network community it's quite known. It's also quite simple concept of convergence because it's very discrete, and it's actually mathematically a notion of convergence on the space of rooted locally finite graphs. The root is important here. You can do this for locally finite graphs. And the way you are doing this is that you localize. That means you take your graph and you just restrict it to a ball of radius k, which means I take this notation that you restrict to all the vertices in distance at most k. And here you see one where you see in red all the vertices in distance less than 3, as far as I can see, 1, 2, 3, yeah, to the root. And the notion of convergence just says if I've given a sequence of rooted locally finite graphs, then they converge to a limiting rooted locally finite graph if for all radii k these restrictions converge in a discrete sense. That means I'm actually only describing what happens around a neighborhood of the root. It's not a global convergence where you see everything and take everything into account. So there's a nice example, very simple one to understand. If I have a linear tree, let's say the vertices 0 to n, which are linearly connected, and I have take as the root 0, which is the left end, and I'm taking the limit, then I clearly will end up in the positive integer line with 0 as the root, the origin as the root. So now what can happen is that you want to take local limits of something which is finite but does not have a root. And then you would like to put it in this framework, so you have to root it. And the way we are rooting this, it was introduced by Benjamini and Schwamm, and it's in the literature referred to as Benjamini-Schwamm convergence. Basically means that we first of all pick a root at random. That means if you talk about the local limit of a sequence of finite graphs, you always want to do this from the perspective of a typical vertex. And here's the slight difference. If I have the same graph, but this time there is no root, the rule is to root at random. So if I take a random root from that set, then basically what will happen that I see to the left of the root and to the right of the root, like a diverging number of vertices. So the local limit will be the whole set, with 0 as the origin. And one thing to notice here, it's also the weak convergence, convergence in law, because the moment that you're picking the root at random, you talk about random graphs, even though the randomness is only in the root in the moment. And that's why it's a weak local convergence here. But of course, what we are mainly interested in will be the weak local convergence if also the sequence of graphs is random. So here's an example of a configuration model like the random three-array graph. In the random three-array graph with an increasing or diverging number of vertices, you first of all pick the root, uniformly, but no matter what you do, the root will have 3 children by default. So if I explore just the ball of radius 1, I will see always this. If I explore the ball of radius 2, then I will see the children of the root and the grandchildren of the root. And then it might happen, if I have bad luck, that the grandchild is actually the root itself, because there's already a circle. But of course, if I let n tend to infinity, I will see this with a probability which goes down to 0. So therefore, this is what you will see for finite 1, 2, 3, 4, 5, ball of radius 5. You will see a 3-array tree, and that means that also the local limit will be the infinite 3-array tree of this model. Okay, so we come, yeah, sure. I'm saying that the random 3-array graph converges locally to the infinite 3-array tree, to a tree also. No?
By 3 array graph, delete 3 for everybody. By 3 array, means delete 3 for everybody.
By 3, I mean everybody has degree 3. Yes. And so you see, this is not a tree, the limit is a tree. And this is the reason for this is that this one, it's a sparse graph. Now, if I have only degree 3 and I let n tend to infinity, I will get something very sparse, and typically for sparse graphs that they have limits which are tree-like. Okay. So there are more interesting local limits, and we have already talked a bit about a complete graph with n vertices. If I'm taking the uniform spanning tree of the complete graph with n vertices, what will happen is that I see the uniform tree with n vertices, as I said, and I told you that it looks the same as a branching tree, which has the Poisson offspring distribution, no matter which lambda, but conditioned on progeny n. And if I let now n tend to infinity, I will see an infinitely long tree. I will see actually a branching tree which is conditioned to survive forever, because before I have conditioned that it has at least n, but if it has infinite population size, one can show that it's equivalent, that it survives forever. So in the first part of tomorrow's class, I will tell you a bit about conditioning branching trees. And for the moment, we look at a very particular one, and this is the so-called Poisson 1 binary branching tree conditioned on survival. It consists of precisely, it's a rooted tree, precisely one line of descent, which goes to infinite. And from that one line, you have lots of trees branching off. And these are family trees of a branching tree with Poisson offspring distribution with mean 1. They are independent of each other. And no, in a certain sense, the result you will see tomorrow will tell, yeah, that's the tree I'm taking here. And the rest I'm telling you tomorrow. The result which we want to use is that if I take the Poisson 1 Benjamin tree conditioned to have total progeny n, then if n tends to infinity, it converges locally. And it's a statement only about local convergence. It will be converged locally to this tree which you see here. Not a branching tree conditioned on survival. Good. And the nice thing is, no, that we are not only can prove this for the complete graph, which is a bit, no, it's always the toy model, but there are much more original results, much more recent results, namely by Azaf, Nachmias, and Yuval Perez from 2002, who say that you can do precisely the same for a regular graph where every vertex has degree d. No, just take, doesn't have to be the uniform graph, it's a deterministic sequence. It's more important that in the nth approximation step, everybody has degree dn. The degrees should go to infinity. And that also in this situation, the local limit of the uniform spanning tree of Gn is this tree which you see here. Now this will be the proof of this, or the sketch of the proof. After we collected all the proofs, will be the content of the talk Ellie will give in the third part on Wednesday. But that's the result. And yeah, you can see that the complete graph is a particular case because here d of n would be n. No? But in that graph, d of n does not have to grow linearly. It doesn't have to be a dense graph sequence. It can be sparse, but just one that goes to infinity for the moment, no? To get the Poisson limit. Okay, so what we will also use in this project is uniform spanning trees on infinite graphs. Now, we have here our simple connected locally finite rooted graphs. And if I want to define the uniform spanning tree on this one, then there are several things to be careful with. And one of them is that on an infinite, or the space of infinite trees, you cannot talk about uniform distribution. No? There will be infinitely many trees spanning this one. You cannot do this. So what you usually do is you define such kind of objects in statistical physics by approximation. And if you want to approximate it, then often you do it from inside, like something exhausting from inside, but it's also not necessary. But even if you do it by exhausting inside, you kind of have to prove that no matter how you approximate, you get at least the same limit. If you get several limits, then you're in trouble and you have to say a bit more about it. And here we are in trouble, we have to say a bit more about it. And I give you just one particular way to do it and tell you why we think it's a very good and very interesting thing to do. No? And kind of the right way. So what we are doing is we look again at the restriction of our graph to a ball with radius n. No? If we do this, that would be a very naive thing to do. And only do this and then take limits as n tends to infinity, which is the free boundary case, then we would not learn anything about what happens outside this one. So now we do a little bit more. We identify everything which is outside this ball. We contract it to a single vertex. And we connect this single vertex with all the boundary points of my graph. So the graph should here be just a box Zn. And if I do so, then I can define the local limit of the sequence. No? The W here stands for wired. My English is not so good, but I think pronunciation wired means that you put a wire to this one vertex, which is outside the box. And you take the uniform limit and you call the limiting object wired uniform spanning. And now you have an F here and not a T. So the F stands for forest, and it goes back to the thing which you can observe, that the limit does not necessarily has to be a tree anymore. It might get disconnected, and it's just a forest consisting of trees. And the reason is that if you have an infinite graph, you might have connections between two vertices which have a diverging distance. No? You might have a hair which has distance 100, and then you have a pair somewhere which has distance 1000, and so on. That means no matter how you approximate by finite boxes, how large the box is, you always might get this connected, and this will show in the limit. And that's why we use this abbreviation, wired uniform spanning forest, for this object. Okay, and of course, there are other ways to do this. I won't talk about it because we mainly use this one in the project, but I would like to emphasize a result by Aldous and Lyons, which can be considered as a continuity result, which tells us that if I have a sequence of graphs Gn which converge locally to G, then the uniform spanning tree of Gn converges locally to the root component of this wired uniform spanning forest. No? It has several components, but only one which contains the root. Now, and this kind of continuity tells us that we probably did the right thing. Because no matter what you do, you converge to that component. And there's another reason, and this is that we can extend Wilson algorithm very natural way and can actually create this wired uniform spanning forest with Wilson algorithm. So that tells us also that maybe that's what we should do. So I already told you that you can adapt straightforwardly, and the recurrent graphs, the only difference will be that you run now time infinite rather than finite, because you have now infinitely many vertices to include into the graph. In the transient case, a problem which might arise is that certain random walks escape to infinity. No? And therefore, we have to modify, in the transient case, Wilson algorithm a bit. And this is that we're taking now the root, no, I think about V0 as the root, to be infinity. It's not clear what infinity is, but it's somewhere, no? Something you need infinite time to reach. And then what you do, you start your random walk as before in some vertex V1, and you run it now until it hits infinity. And as I said, it's infinitely far apart, you need infinite time to hit it. So you just run it infinite time. And this way you get an infinitely long path, and then you loop erase it in the order of appearance. Remember, loop eraser you can do for transient walks. And then you get an infinitely long path which has no loops. And this is something which you have seen already in the conditioned branching trees also, this infinite line of descent. So it fits kind of very well. And then you do what you did before. You start with the second vertex, V2. You let run your random walk independently of what happened before, starting in V2 until you hit this branch T1. And more general, conditionally on that you have K branches already generated, you pick the K plus first vertex. You run your random walk independently, starting in VK plus 1. And then, once you have hit this point, you always loop erase, and then you just glue it together with the tree before, and you continue until all vertices are in the tree. Of course, this takes now infinite time if the tree is infinite, but this way, the Wilson algorithm, it's very neatly extended in a very natural way, and the good news is that the output is precisely the wired uniform spanning forest on G. Okay. Good. And so time is almost over. Anyway, we reached the point where I can tell you a bit about the problems the people in the group are working on. The main motivation for the project is to study local limits of uniform spanning trees of a configuration model. I won't have time to tell you this in a lot of detail what it is. Just take it as the uniform random graph for the moment with a prescribed set of vertex distributions. No? You know the degree distribution, and you want from such a model the uniform spanning tree limit as something happens. In this particular case, we want that the degrees go to infinity, similar to the D regular graph. And we will not do this directly in the group, at least not this week. We will start by studying a slightly easier model, which is the wired uniform spanning forest of a sequence of supercritical binary branching trees. And the reason why we are doing is that under some nice conditions, the root component of the wired uniform spanning tree of such a sequence of branching trees should describe the uniform spanning tree local limit of a corresponding configuration model. This is also something, it's not on the list of things to do, which the group will do, but they won't do this in the first 2 weeks, to establish this link. We start slowly. We start with a sequence of branching trees where the offspring distribution goes to infinity. which means that the support goes to infinity, not a probability that you have a number of children in a compact set will go down to 0. And once you have done this, you start with the model which we already know from the literature, a DN-array tree or D-array tree. We take the wired uniform spanning forest. We look at the component that contains the root. And then we have a sequence of these rooted locally finite trees. They are random, and we take the limit as the degrees go to infinity. No? The result is known. It goes back to Hagström. I think you proved it first, but with very different methods, not even using Wilson algorithm. So the point is understand the proof with the Wilson algorithm and be able also to write down the technical details so that we know what we have to be careful if we modify the result. Second, start playing with the things, do simple calculation, change the requirement of D-array, maybe say that with each vertex has this probability half degree D and this probability half the degree 2D. Study then exactly the same, let D tend to infinity. We did the sample calculation. We found that you get the Poisson-Benjamin tree conditioned on survival, where now the Poisson distribution has a random intensity. Here's the random intensity distribution, the law of it. You can see that the mean, of course, is 1. No, it should be 1, but it's just random. The mean intensity is 1. And once you have a lot of examples, you have probably also conjectures, and you might think about universal limits. You might think about under which conditions on these offspring distributions you obtain a branching tree with Poisson offspring distribution and the random intensity conditioned on survival. And if it's not always possible, you might think about what else could happen. And you can, of course, also think about whether the D-regular tree is the only one where the random intensity is deterministic, namely 1, or whether there are other models where you reach this deterministic intensity and also try to characterize the sequence of these offspring distributions. And that's enough for today.
Any questions?
Any notions of stability in terms of local stability for the theory key generation state? How long to have how should n behave so that the first key generation has stability? Because it's connected with random walks.
It's a good question. Yeah, it has to do with random walks, but I don't know the answer like ad hoc. No, they are two different models. The only feature they have together is that they don't have loops. No. I think among all these models of statistical mechanics, the loop-based random walk is very easy to study, and that's why we have this Wilson algorithm, but other than this, there's no nice way to generate self-avoiding random walks.